Mine will probably be less than 10 minutes, I'm sure. I've just got a handful of slides. So I wanted to show this initial one to describe a tool that I wrote based on traceroute. So hopefully all of you know how traceroute works, where you send a packet and you increment the TTL at each hop, and you get a response from each router until you reach the destination where you'll get a port unreachable or an echo response back depending on the protocol you're using. What you get back is the ingress interface on the forward path. So on these routers, on the path, you get the response from that A interface along the way. But what I was wondering is if I could actually get that B address along the path and build a full path of all the interfaces to the destination. So how do you do this? So I ended up discovering that you could, and maybe this is novel and someone's done this before and I didn't find it and I apologize, but what I discovered is when you get that A interface address from that second hop router, that middle router, you know or can presume that that A address is on the same network as the preceding B interface on the first router. And so it's a simple matter of discovering that B address. And so you can do essentially a ring search where you go one address greater, lower, then two higher, two lower, until you find it. And the trick is to use a TTL of the preceding router to discover that address. So when you send a probe with a TTL of 1 with an address that should be in the range of that A interface on the second hop router, if you get a response, you can presume that you found that egress interface on that router. And so you do that along the path, and then you discover your interfaces along that path. And so that's, I wrote something called trace interface, and this is sort of what the default output looks like. So if someone from Merit here can tell me if this actually looks right. So you run this, of course you need root privileges to get access to the sockets. My output is not exactly intuitive, but the last hop, I believe, is actually, the last line there is actually what would be the default gateway for the Nanog web server. So the arrows indicating the direction of the hop there. And so why might this be useful? I just thought it was kind of neat. Maybe it's not all that useful, but it might be useful for just discovering topology a little further than you would otherwise have. But maybe there's something here that you could use to also pinpoint exact delays, and whether it's the actual link or the router itself. Something I discovered was that this doesn't work so well with your typical trace route on Unix, which uses UDP. If you aim packets to a destination address of a router using UDP, they just tend not to respond. You tend not to get anything back, so ICMP just tends to work better. And from most of the experiments I've done, and it hasn't been a lot, your router interfaces, which would make sense, the neighbor addresses tend to be one away from each other. So people who are addressing usually in /30s between the routers. But occasionally you can have your spreading range go a little further, and you can discover if it's /24, you can certainly sweep that range as well. So I put some prototype code here if anyone wants to play around with it. I'm not much of a programmer. My standard joke is I don't know Perl, I know combat Perl. So it's something that mostly works, not completely works, but it's something you can certainly play around with if this is of interest to you.
Excellent. Thank you. That was lightning. Are there questions?
Hello? I just have one comment, which is that another technique which the academic community has found to be useful here is actually reverse DNS lookups, and finding that many times you can tell from the base name of the router in the DNS response, actually, the base name of the router is the same, and it's, interface 1, 2, or 3, whatever, on that base router name.
Sure.
So this is pretty cool stuff, though.
Excellent. Thank you.